So, like I was saying, I said a rectifier is an electrical component that converts alternating current to direct current. And the process of converting alternating current to DC current is known as rectification. So there are two classifications of rectifiers. We have two classes of rectifiers. The first one is half-wave rectifier. The second one is full-wave rectifier. So as the name implies, the half-wave rectifier is a type of rectifier which converts half of the AC input signal into a pulsating DC output signal. And the remaining half signal, which is the negative signal, is blocked in that phase. While in the full wave rectifier, it converts the full AC input signal, that is both positive and negative half cycle, into pulsating DC output signal. Now, if you go through the next slide, you see, unlike the half-wave rectifier, the input signal is not wasted in full-wave rectifier. So full-wave rectifier has a higher efficiency. We have positive half, we have negative half. So at one cycle, for half-wave, the negative half is lost, only the positive half is taken. But for full-wave rectifier, the two halves, the negative and the positive half, are considered at each cycle. So a half-wave rectifier is the simplest form of a rectifier that requires only one diode for the construction of such rectifier circuit. So for half-wave rectifier, we have, or what we need, the components that we need are basically three: a diode, a transformer, and a resistive load. So this is a diagram of the circuit. So here we have a transformer. We have the primary side and the secondary side. And then we have a diode and a load. So the load refers to our electrical gadgets. So the power is supplied from the mains, and then it's stepped down after passing through the primary part. Is primary section of the transformer. It is stepped down to the secondary and then follows the diode where it is where the voltage or current supplied is reduced further. So assuming that this load attached is 15 volts, so and 220 volts is supplied. So at this transformer side, it will be reduced to maybe like 100 or 110 volts to the secondary, and then 110 volts passes through the diode. So through the diode, it is stepped down further, it is rectified, it is reduced further. Only 15 volts is allowed to pass through the diode to power the load, our electronic device. So that is how it works. So this is a waveform of the input and output of half-wave rectifier. So remember that AC are sinusoidal. So look at it. It comes in full sine wave, enters through the supply to the primary and then secondary, move to the diode. But by the time it comes out, the negative half is cut off. So we have a pulsating DC output. Only the positive terminals our positive waveforms are out. So that is a half wave rectifier. So this is a waveform showing what really happens here. You see the supply voltage, which is V in, goes in to the source, and then the positive side as shown, but the negative sides are cut off. All the negative sides are cut off. Half-wave rectifier capacitor filter. Now, the output waveform of half-wave rectifier, like we said, is a pulsating DC waveform. So when signals are pulsating, there is tendency that it can destroy the device. Pulsating, like fluctuating, is not stable. So in order to make it stable, a filter is added. That filter in the form of a capacitor is connected in parallel to the load. So the filter will filter off every unusable signal and allow only the useful signal to go to the load. That is the essence of the filter. So the circuit diagram below shows how a capacitor filter is used with half-wave rectifier to smoothen out a pulsating DC waveform in a constant DC into a constant DC waveform. So now, if you look at the diagram here by the left and by the right, you see DC without capacitor and DC with capacitor. So here, note the filter is made up of a combination of components such as capacitor, resistor, and inductor. The capacitor allows an AC component and blocks the DC component. The inductor allows the DC component and blocks the AC component so that they don't interfere. They don't overlap. The AC does not overlap into the DC, and DC does not overlap into the AC. So both of them are like gates. Now, half-wave rectifier formula. We have the ripple factor of half-wave rectifier. Ripple factor determines how well a half-wave rectifier can convert AC voltage to DC voltage. So ripple factor can be quantified using the following formula. So the ripple factor we are talking of is like the pulsating signal that is given out at the output. So here we have the formula gamma is equal to VRMS over VDS. VRMS, you know, that's the AC, while VDS is the DC, all bracket square minus 1. So the ripple factor of half-wave rectifier is just about 1.21. Efficiency of half-wave rectifier, that is power output over power input. The power output is the DC because the AC comes in at the input and then is converted to DC. So the DC is the output while the AC is the input. So efficiency is always output over input, the ratio of the output over the input. And this time, the output is the DC power, while the input is the AC power. The root mean square value of half-wave rectifier. This is a normal formula. RMS equals to IM, that is I maximum over root 2. And then form factor of half-wave rectifier. The form factor is the ratio between the RMS value and the average value, and is given as RMS value over average value. So this could be the current, it could be the voltage, because in current you have RMS value, as well as in voltage you have RMS value and average value as well. So application of half-wave rectifier. They are used for signal demodulation purpose. They are used for rectification application. They are used for signal peak application, and their disadvantages. Power loss. Remember, we mentioned this. It has two half coming in waveform from the AC source. However, the negative half is lost because it uses only one diode for rectification. So the negative half is lost. So there is a power loss, low output voltage. The output contains a lot of ripples, The pulsation is too high. Now, the next type of rectifier is a full wave rectifier. A full wave rectifier is defined as a rectifier that converts the complete circle of alternating current into pulsating DC, unlike half-wave rectifier that utilizes only half of the input AC circle. Full wave rectifier utilizes the full circle. The low efficiency of half-wave rectifier can be overcome by the full wave rectifier. Remember here, one of the disadvantages is power loss and low output voltage. So if the voltage at the output is low, it means that the power will be low. And if the power is low, that is at the output. Remember, the efficiency is output power over input power. So if the output is low, the efficiency will be too small. That is the numerator. If the numerator is low, the output will be, the efficiency will be small. But if the numerator is high, the efficiency will be large or big. So, and that is because of just the single diode rectification that is used in the construction of half-wave rectifiers. But in full wave, we have two or more diode carrying out the rectification. And so no signal is lost. Both positive and negative half circle is being used, is amplified, or is rectified. So the circuit of the full wave rectifier can be constructed in two ways. The first method uses a center tap transformer and two diodes. This arrangement is known as center tap full wave rectifier. The second method uses a standard transformer with 4 diodes arranged as a bridge. This is known as bridge rectifier. So under full wave, we have the center tap full wave rectifier, and we have the bridge rectifier. So here, if you look at this simulation, you will see Now this is one half, this is another half. So look at the input voltage, that is the Vs at the top here, where the mouse is. When this voltage is supplied, it comes in sinusoidally and comes in direct, one half. This is the second half. At the output voltage, you see that there's a complete sine wave. Though you are not seeing any negative one, but there is no gap in between the sine wave. The negative we see at the input signal has been converted to a useful signal out there. So that's why you see 1, 2, that is 1 up, 1 down, making 2, 1 up, 1 down, making 4, 2 positive, 2 negative here in the input, but at the output you see them as 4 positive sine wave. So that is a full wave rectifier, a full wave rectifier in one half, then you see it go back again in the second half. So both negative and positive half is utilized. So this is another simulation. This is what happened in the first half. 2 diodes are occupied in the first half. Then the second half, another 2 diodes are engaged. The first half engages 2 diodes. The second half engages another 2 diodes to rectify what we do. So this is how full wave works. So here we have a center tap full wave rectifier. So the center tap is that the transformer, the secondary part of the transformer at the center is tapped. That is where the voltages flow. So it goes in, comes to this side, and moves back. So look at the waveform. The input voltage waveform. So where the first half goes in through D1, the negative half goes in through D2. The first half, that is the positive half, takes care of the positive sine waves, while the negative half takes care of the negative sine waves. And both of them come out at the output as both positive. So if you put them together, the top one on the right here, the waveform, you see the top one is the positive half. The middle one is the negative half. If you put them together, the third one gives you the output. That is the final output of the wave voltage waveform. So this is how it works. So the working of full rectifier is here. You can read them. Like I've explained before, so during the positive half cycle, diode 1 is forward bias as it is connected to the top of the secondary winding here. So during the first half, this is forward bias, while diode 2 is reverse bias as it is connected to the bottom of the secondary winding. Due to this, diode 1 will conduct acting as a short circuit, and diode 2 will not conduct acting as an open circuit. Yeah, so if you look at this diagram, if you look at the arrow, the direction of the arrow, you will see that for diode 1, when it's at the positive half, you see diode 1, the arrow of current moves. Diode 2 is reverse bias in that way. So the current will not flow through that. While in the second half, the current will flow through diode 2 and then move up. Diode 1 current is coming, diode 2 current is coming. At this junction, they meet and then form a combined current. That is why you have I is equal to I1 plus I2. I1 plus I2. So during the negative half, diode 1 is reverse bias and diode 2 is forward bias because the top half of the secondary circuit becomes negative and the bottom half of the becomes positive. Thus, in a full wave rectifier, DC voltage is obtained for both positive. So if you look at this diagram, you see a positive and a negative at the top, a negative and a positive at the base. So when the top is positive, the bottom is negative. That is the first half. When the bottom is positive, the top is negative. That is the second half. That is the second half. So at the first half, the top is positive, the bottom is negative. So if the bottom is negative, it's reverse bias. The current does not flow through there. Now, at the second half, the top assume negative and the bottom assume positive. And current flows through only D2. And D1 becomes like a reverse bias diode, and current will not flow through that. Peak inverse voltage. Peak inverse voltage is the maximum voltage a diode can withstand in the reverse bias direction before breaking down. And the peak inverse voltage of a full wave rectifier is double that of half wave rectifier and is sometimes given an acronym of PIV. PIV. So the PIV across D1 and D2 is 2 Vmax. DC output voltage, the following formula gives the average value of the DC output voltage. We have the DC output voltage at the average current times the load resistor. And of course, the average current is 2 Imax over pi. 2 Imax over pi. That is the formula for average current. For average voltage, it is 2 Vmax over pi. 2 Vmax over pi. The RMS value of current can be calculated. We saw this in previous slide. RM is equal to Imax over square root of 2. Then the field factor is RMS value of current over average value of current. That is the field factor. The field factor here is 1.11, but for half wave is 1.21. The same formula can be applied to voltage. Here we have average or DC output voltage. So the average DC voltage is this VDC, that is the DC voltage is equal to the current, DC current times load. DC current times load. And is given as Imax over pi times the load. So the efficiency is still the same formula. Output power over input. Output power over input power. The output is always DC, while the input is AC. This time the efficiency is 81.2%. 81.2%. Advantage of full wave rectifier. The rectification efficiency of full wave rectifier is double that of half wave rectifier. The efficiency of half wave rectifier is 40.6%, while the full wave is 81.2. The ripple in full wave rectifier is low, hence a simple filter is required. The value of the ripple factor is in full wave rectifier 0.482, while in half wave rectifier it is about 1.21. The output voltage and the output power obtained in full wave rectifiers are higher than that obtained using half wave rectifier. Of course, that shows why we have high efficiency. The only disadvantage of full wave rectifier is that they need more circuit elements than half wave rectifier, which makes them more costly. So because here we need two diodes. We need two diodes, and this is a center tap. For this, for full wave bridge, we have 4 diodes. So definitely this will be more expensive than when you are making use of just one diode. So the price is almost double or more. So the bridge rectifier, we have seen how the bridge rectifier works. So a bridge rectifier circuit can be built with 4 diodes, which are used to change both input AC half circuit to DC output. So in this kind of rectifier, the 4 diodes are mainly connected in an exact form. In the positive half circle of the bridge rectifier, the 2 diodes D1 and D2 will become forward bias, whereas D3 and D4 will become reverse bias. From a closed loop, the diode D1 and D1 will provide a positive output voltage across the load. So here, we've seen the demonstration here. So this is D2, D1. So in one half, this is working, D1 and D2. And if you look at it, when the current enters through this point, I hope you are seeing the mouse. When the mouse pointer, when the current enters through this point, it goes. Remember, the diode conducts or allow current to flow through it in only one direction. So it goes through the back here, come to this point, and goes in. So when it gets here, these 4 and 3 are like reverse bias. Current cannot come back here, so it will flow directly this way. Then here, the second half, it comes through here and pass through 3 to 4. When it gets here, it cannot go back because this is reverse bias. So it will flow through to this direction. So that is what happens here at point C. When the current enters, it will pass through D2, get to A1, okay, get to A, move to D1, and then move to the pass through D1 and get to D. When it gets to D, it will follow D, the middle line, pass through RL. Then at the second half, it comes to this C again, then pass. When it comes at second half, D2, D1 are seen as reverse bias. So it will come through this and pass through and come through 3, get to B, pass through 4, get to D, and then follow through RL. Now, that circuit is a bit different from what you find below. What you find below is similar, but here the load is connected in between the 4 diodes. But here the load is connected outside the diode. So when the current comes to D1, that is the junction between D1 and so in this circuit, we'll see A4 and D1 as positive half and D3 and D2 as negative half. That is the second circuit. So as positive half, D4, D1 conducts, it gets to the junction of D1 and D2 and then flow forward and pass through the load resistor. Then for second half, D3, D2 is positive, 4 and 1 are negative, and it goes through, again, get to the junction, pass through RL. So the explanation is here. The result in diode D1 and D3 becoming forward bias, while D2 and D4 is forward bias. That is for this circuit. So you have to understand the workings of the circuit. You don't have to cram it. The arrangement of the diode is what you follow to study different rectification circuit and see how the diodes are arranged. So, and see so if you look at this, here you see D2 and D4 are positive at a time, and D3 and D1 are positive. At a time. So this is the output waveform. Now, characteristics of bridge rectifier. We have the ripple factor. We've talked about the ripple factor before. So each of these rectifier have their own ripple factor. For this, the ripple factor is 0.48. The efficiency is the same as the efficiency of the center tap, the full bridge center tap. So here you have advantages and disadvantages. So let's look at it. The efficiency of the bridge rectifier is higher than the efficiency of half-wave rectifier. However, the rectifier efficiency of the bridge and center tap is the same. The DC output signal of the bridge is smoother than the output DC signal of the half-wave. Of course, that is expected. In a half-wave rectifier, only one half of the input is used. We have talked about this. Disadvantage. The circuit of a bridge rectifier is complex when compared to half-wave rectifier and the center tap full rectifier. Bridge rectifier uses 4 diodes, while half-wave rectifiers and center tap full-wave rectifier uses only 2 diodes. So this is a major disadvantage because it means that the cost of bridge rectifier will be 4 times half-wave rectifier and 2 times center tap rectifier. When more diodes are used, more power loss occurs. In a center tap full-wave rectifier, only 1 diode conducts during each half circle. But in a bridge two diodes connected in series conduct during each half cycle. Hence, the voltage drop is higher in a bridge rectifier. So applications. A rectifier is used for powering appliances. They are used for transformers, used while soldering. It is also used in AM radio, in circuit, it's also used for modulation. It's also used in the voltage multiplier. Other applications, isolating signal from a supply, rectifying a voltage, such as turning the AC into DC voltage, control the size of a signal, mixing signal, detection of signal, lighting system, and so on. So here we have an example, the applied input AC power of a half-wave rectifier is 10 watts. The applied input AC power to a half-wave rectifier is 10 watts. The DC output power obtained is 40 watts. What is rectification efficiency? What happens to the remaining 60 watts? So with this question, you have input of 100 and output of 40. So the rectification efficiency will be output over input. That is 40 over 100. So 60% is lost. What happens to it? It's lost. Two, an AC supply of 230 volts is applied to half-wave rectifier circuit through a transformer of turn ratio 10:1. Find 1, the output DC voltage, 2, the peak inverse voltage. Assume the diode to be an ideal diode. So you have the supply voltage given, you have the turn ratio 10:1, you have to find the output voltage, DC voltage, at the PIV. So the ratio of the transformer is 10:1, which means that the primary side is 10, the secondary side is 1. And there's a relationship between transformer and voltage. The primary, that is VP over VS is equal to NP over NS. So if we know NP and NS, which is NP for primary turn, NS for secondary turn, and we know the primary voltage, we should be able to use the relationship to find the secondary voltage. So that is what we have there. But before we do that, this voltage given is AC voltage. We have to find the root mean square of that voltage. This is AC, which is the root mean square. So we have to find the equivalent of that voltage. the primary voltage, which is the primary voltage is the Vmax. Remember here, this formula, I said this is current, but we can also have a voltage conversion. Vrms is equal to Vmax over square root of 2. So we are given the voltage Vrms, which is 230. We need to convert it to Vmax to be able to find the secondary current. So Vrms times square root of 2 will give us our Vmax. So that is what is done here. So our Vmax, that is the primary, on the primary side, is equal to 2 root 2, square root of 2 times the main supply Vrms value. So that gives us 325.2. And then when you substitute this value into the equation relating primary and secondary turn to voltage, primary and secondary voltage, that will give you the secondary voltage as 32.53. And then we are asked to find the peak inverse voltage, which is PIV, which is this. Remember, we have the peak inverse voltage here. Peak inverse voltage here. So we need to find our current and then substitute to find our peak inverse voltage. So the direct current is equal to Imax over pi. And then the DC, VDC is equal to Imax over pi times L. So our Vmax Rm by Ohm's law, V is equal to IR. IR. So the value, the parameters we have at the numerator, IMRL is our secondary, that is what our secondary part of the transformer is given out. Here, at the secondary part of the transformer here, the current that comes through this part is the Imax times the load. That is what we are getting here. In front of the load, we have this. When this current comes out from the secondary part, it comes to this load. So that is what we have. So if you apply that knowledge here, we have our secondary voltage divided by pi gives us the PIV. So you have other about 7 more exercises or examples on this slide. So let's move on to the next. So we are looking at FET. So this is the last topic next week, Dr. Isabel will take over. So FET, which is field effect transistor, is a kind of transistor, unlike BJT, that is current control. You know, in BJT, the IE, that is emitter current, is what determines the output current. That is why we have IE is equal to IE is equal to IB plus IC. So this formula is very prominent in BJT. Without this formula, nothing works in BJT. And this formula simply means that the input current, this is the input current for, okay, it depends on the configuration, but let's say common emitter or common base. So this is the input current. And then this is our output current. So it is this current that controls what comes here. And of course, for amplification, you remember that I said for amplification, the transistor must be connected in active mode. And if it's in active mode, most times, most often, the emitter base junction is forward bias. Emitter base junction is forward bias, while collector base junction is reverse bias, irrespective of the configuration, whether it is common collector, common emitter, common base. In most cases, the emitter base junction is forward bias, the collector base junction is reverse bias. So the input current always determine what happens at the output. That is for BJT, but it's not so with FET. In FET, this time is voltage that controls the input current. The voltage that controls the input current. So let's move on quickly. So like in BJT, we have 3 terminals as well. We have emitter, we have base, and we have collector. So if you look at those 3 terminals grammatically by their name, emitter emits, collector receives, base, that is like a platform through which the collector receives, base, something that is like a foundation, a base that allow other material to rest on it. So the base is like the platform by which the collector receives from the emitter. So if you look at it in the light of FET, we also have 3 terminals: gate, drain, and source. Gate, drain, and source. Like I said before, for FET, it is a voltage control device where the input voltage controls the output current. In FET, current used to flow between the drain and the source terminal. This is the gate, this is the source, and this is the drain. So the current flows from the source to the drain. And sometimes it could flow from the drain to the source, but it's just a channel. It could go up, it could come down. So this current that flows from drain to source or source to drain is controlled by applying voltage between the gate and the source. So the voltage between the gate and the source controls the current that flows up from the source to the drain. So this applied voltage generates the electrical field within the device, and by controlling this electric field, we can control the flow of current through the device. Now, if you look at the construction of BJT, we'll say that you are like bringing two PN junctions, connecting them back to back. But in this case, we don't have that kind of back-to-back connection. However, we have, for N channel, we have two P's by the side, connected internally. Though by this structural diagram, you see the P on top, but within the system, the two P's are the same because they are just connected by a wire within the system to become one. But outward, they are positioned at the end. So the gate source voltage will control what will happen to the P's, whether the P will be expanding or it will be collapsing. So it depends on what happens between the source and gate, the voltage applied between the source and the gate. You understand better when we move. So comparing difference between BJT and FET. BJT is called bipolar because in BJT we have two charge carriers. We have holes and electrons as charge carriers. Electron may be the majority charge carrier, while hole is the minority charge carrier, or electron may be the minority charge carrier, while hole is the majority charge carrier. It depends on the configuration. For NPN, electron is majority charge carrier. For PNP, hole is the majority charge carrier. But it's not so with FET. FET is a unipolar device. FET also has holes and electrons, but it does not work like minority and majority. It works with only one carrier at a time. So if the channel is a P and the ends are N, that is, by the side we have N, and at the center we have a P, then it means that it is hole that is conducting, that is charge carrier. But if, as we have it in this diagram, this is N channel, for N channel, only electrons are charge carriers. For P channel, only holes are charge carriers. So both of them have three terminals. The BJT has an emitter-based collector. The FET has source gate drain. BJT is current control device, while FET is voltage control device. BJT is bipolar, FET is unipolar. BJT has two types, NPN and PNP, while FET has two types. We have JFET and MOSFET. FET. The bipolar junction has two main disadvantages, and that is BJT. It has a low input impedance. Low input impedance in the sense that the input side is always forward bias, especially for amplification, is forward bias. So if it is forward bias, it means that the boundary, that is the junction, has a very small resistance to the current that is coming from the source. So it has a small resistance. It's only with reverse bias that you have a high resistance. When a junction is reverse bias, you have a high resistance. But when a junction is forward bias, you have a low resistance. So for BJT, the input side is forward bias, and so the impedance, the resistance there is low. And that also has to do with the noise level. So because of that, it has a considerable noise. So BJT produces noise. And when you use it for sound system, that is when you will always hear the noise. To overcome this problem, that is why FET was introduced. So FET has high input impedance. Why is it high input impedance? Because this time it is voltage that is controlling, and the voltage is reverse bias. At the input, the voltage is always reverse bias, unlike the BJT that at the input, the biasing is forward. But for FET, at the input, the biasing is reverse. So it gave that, or gives it a high input impedance. And that also lead to low noise level. So it has a low noise level. We've talked about this briefly, but there are two types of FET which I've mentioned before, JFET. So in JFET, we have the N channel and we have the P channel. In MOSFET, we have the depletion type MOSFET and the enhancement type MOSFET. So by the right side, you see the N channel, JFET, and below you see the P channel, JFET. Now, if you look at the biasing, that is the application of the voltage there, you see that it is reverse between gate and source. The voltage is reverse bias. With respect to the source, the voltage is reverse bias. Features of JFET. JFET is a voltage control device. Input voltage, VGS, controls the output current ID. In JFET, the width of the junction is used to control the effective cross-sectional area of the channel through which the current conducts. This is the width of the channel. It is what controls. Now, if this reverse bias is increased, I will explain it later again. This P, the two P's at the side, will begin to, when you reverse bias a junction, the more you reverse bias it, the more the depletion region will expand, 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 expand. So the more the reverse bias, these P types, which form a depletion region between the N type and P type, will expand. So while it's expanding, this channel will be closing up because the P will be extending into the channel, both sides. And at a point, the two P's on both sides will close up that channel. So when that happens, current will not flow again. So it is always operated with source gate PN junction in reverse bias. Because of reverse bias, it has a high input voltage. In JFET, the gate current is 0. The gate current is 0 because the gate source is always reverse bias. Gate source is always reverse bias. Construction of N-type semiconductor, JFET. Major part of the structure in N-type material, the top of the N-type channel is connected through an ohmic contact to a terminal referred to as drain. So here, this complete is like N-type semiconductor material. Then at the top here, a terminal is deposited here to make it a drain. At the base here, another terminal, ohmic terminal, that is conducting material, is deposited to make it a source. Then here, another terminal is made, the gate terminal is made. Then the P-type is fabricated by the both sides, which form a depletion region. Which forms a depletion region. Give me a few minutes. The internet here is fluctuating. It will soon come on. Okay. So the P-type on both sides of the diagram there, you see, are connected internally using an ohmic contact. So what affects the p-type on the left also affect the p-type on the right. So both of them are affected at the same rate. Now, when the gate source voltage, VGS, is applied, and the drain source voltage is 0, that is, as it is here, the first diagram, there is no voltage source on both sides. Unlike here, where you have voltage VGS and voltage VDS. But here, when there is no voltage at all for both sides, the VGS is 0, the two depletion layer and channels are formed normally. When VGS increases negatively, remember that it's a negative bias. Is a negative, the VGS is negative bias. So when it is increased negatively, that is from say -2 to -4 to -6 to -8 to -10 and so on, the depletion layer are also increased and the channel becomes decreased. So if you look at these three diagrams, you see that for the first one, there is no application of voltage. The second one, voltage is applied, and when we increase the negative voltage, increase the voltage, the bias negatively, you see the channel is decreasing because the depletion region is increasing. When you increase a reverse bias junction, the voltage across a reverse bias, when you increase it, the depletion region will expand. So that is what is happening in the second diagram. When the depletion region expands, the channel closes, decreases. Further increase of the reverse bias now make the depletion region to close the channel. So both p-type on both sides, the b-type on both sides have expanded. The depletion region has expanded, and then they have closed the channel completely. So at this point, current will not flow from source to drain again. So the voltage at which this channel is blocked, where current does not pass again, is called the VGS off. That is a cut-off voltage. Note that cut-off voltage is called VGS off. VGS off. Now, when VGS is 0, that is, remember here, there is no VDS. There is no voltage across the source and the drain. It is only voltage across the gate and the source. So this time now, we are looking at when there is no voltage across the source and the gate, but across the source and the drain. I'm trying to correct something. So three things happen when VGS is 0 and VDS is increased. So we apply voltage across the drain and the source, and then we increase it from 0 to a more positive voltage. So if you look at the 2P type by the side, look at the shape. It's different from this. Here we have a uniformity in the shape. Both P types are expanding at the same rate, having the same shape. But here, they are not having, that is the up and the down. The shape here is different. You notice that the up is closing up faster than the down. So the more we increase the VDS, the more the depletion region increases, but the upper part will likely join together before the lower part. And the lower part may not or may. It depends on the applied VDS. So a depletion region between P gate and N channel increases as electrons from N channel combines with holes from P gate. Increasing the depletion region decreases the size of the N channel, which increases the resistance of the N channel. Even through the N channel resistance, even though the N channel resistance increases, the current ID, that's not from the source to the drain through the channel, is increasing. This because the VDS is increasing. Now, let me explain this to you. So when we increase the VDS, the upper part will be increasing. The lower part also will be increasing, but the rate at which the upper part will be increasing is faster than the lower part. Initially, there will be no resistance like this. If you see a channel like this, remember from Ohm's law, V is equal to IR. So when V is increasing, I is increasing, R will be constant. If you look at that formula, V is equal to IR. All of them cannot be increasing. Let's say from the Ohm's law, V is directly proportional to I. That is, the applied voltage across a conductor is directly proportional to the current flowing through it. That is Ohm's law. So V is directly proportional to current. V increases, I increases. So V is directly proportional to current. If we remove the proportionality sign, let me take it back and just put a 1-2 formula there for you to see what I'm trying to explain. Where is this? So we have V directly proportional to I, according to Ohm's law. If I remove this direct proportionality sign, it gives me V is equal to IR. Now, R takes the form of a constant, isn't it? By this Ohm's law formula. So by the Ohm's law formula, V is directly proportional to I, which means V increases, I increases. V increases, I increases. What's happening? Why is this thing turning off on me? V proportional to I, V is equal to I. Listen to me attentively, so that you don't get confused. So by this formula, V is directly proportional to I, V increases, I increases. So I remove the proportionality sign, I replace it with a constant. So R here in this expression represents a constant. So if I apply this knowledge to this, what is happening here, as I increase this V, that is VDS, as I increase this, ID will be increasing. IS and ID are the same. Don't make mistake of thinking they are different. It's just one channel. They are the same. ID flows when it gets to IS, it goes out and continue. So V increases, I increases, meaning R is constant. The channel is open. R is constant. But when you keep increasing VDS, it will get to a level. Then R will begin to increase. When R begins to increase, of course, you know that these two parameters cannot increase at the same time. If V is increasing, I is increasing, R will remain constant. If V is increasing and R is increasing, I cannot also increase. I must remain constant for R to increase. I hope someone is getting what I'm trying to explain. So, as we increase it to a level, once R starts increasing, I will remain constant. Now, the maximum voltage attained for I to remain constant, that is what we call the pinch off voltage. Pinch off voltage. That is this. Pinch off voltage. Pinch off voltage. So at the point we have this. So when VDS is equal to VP, that is pinch off voltage, I will remain constant. I will remain constant. So if you read this, you will see most of them explained. So the drain source voltage, look at it by the side, above which drain current becomes constant, is known as the pinch off voltage. I plot a characteristic graph, like I explained to you during the study of BJT. The characteristic IV characteristic is basically the current and the voltage, while one of the voltage remains constant. So in this case, we keep VGS constant, we vary VDS and get different values of I. So if you look at this diagram, here, look at the movement of my mouse. You see that bold blue side by the by the vertical axis. You see ohmic there. It means at this point, it obeys Ohm's law. Then at this point, you have a pinch-off region and you have a saturation region. So the pinch-off region is the point where the current remains steady, constant. The point where the currents become constant directly down to the voltage bar. That is where you have a VP, and then the current remains constant. And then when we keep increasing VDS, it will get to a point then the depletion region will not be able to withstand the voltage again, and then there will be what is called a breakdown. So we have a breakdown region as well. So this is another graph showing. Now, the maximum current, if you look at this Ohm's law, if you plot a graph of V against I, and you have a straight line, that is Ohm's law. Here we have Ohm's law being obeyed until it gets to this peak. That is, as V increases, I is increasing, V is increasing, I is increasing until it gets to a maximum voltage where I becomes stable. So that maximum current at which the current remains stable is VDSS. That is VDSS. Note all this. Then the voltage at that point is their pinch-off voltage. So you have a transfer characteristic graph here as well. Advantage of FET, we have talked about it a little bit. It is simpler to fabricate, smaller in size. It has a longer life and higher efficiency. It has high input impedance. It has negative temperature coefficient resistance. It has a high power gain. Disadvantage has a low voltage gain. A low voltage gain. Of course, voltage gain is output voltage over input voltage. So if the input voltage is high, output voltage is low, it means that the voltage gain will be very small. They are more costly than BJT. It has no switching time compared to BJT. Special handling is required during installation. Application as amplifier, oscillator, analog switch, integrated circuit, and buffer amplifier. So let's look at some mathematics of JFET. You already know what ID is. The relationship between IDSS and VP. We already know what VP is, which is the pinch-off voltage. We know IDSS, which is the maximum current at pinch-off. So now, the pinch-off voltage, we have talked about VGSS off. VGSS off, that is when we apply voltage across the gate and the source and increase that. Remember that that is reverse bias. So when we increase that reverse bias negatively, keep increasing it, as we're increasing it, the depletion region is expanding, and we get to a point where the two depletion regions on both sides join together, closing the channel. So the voltage at which that happens, whereby prevent the current from flowing through the channel, is our VGS off. Now we compare that to P, which is pinch off. So remember that at pinch off, that is the maximum current attained, and then the current remain stable. Even at pinch off, you see that here at the top, the depletion regions are joined. So it has a relationship with VGS off. So here we have that VGS off is equal to, or the negative value of VGS off is equal to the positive of VP. Or we can say VP is equal to the magnitude of VGS off, because VGS off is always negative. VGS off is a negative. It's a reverse bias voltage, so it's negative. It's negative. So the negative value or the magnitude, when you find the magnitude, you are in a way taking off the negative sign. So the magnitude of VGS off is equal to VP. Is equal to VP. So here it's written here, for example, if a JFET has a VGS off is equal to minus 4 volts, then the VP is equal to 4 volts. So calculate ID. This is the formula. IDSS in bracket 1 minus VGS over VGS off, all in raised to square. ID is the drain current at given VGS. IDSS is the shorted gate drain current. VGS gate source voltage. VGS off is gate source cut off voltage. So here you have different, you have the definitions for all these parameters: IDSS, pinch off voltage, the gate cut off voltage, and the diagram here shows them all. So let's look at this example. The figure here shows the transfer characteristics of a curve of JFET. We are asked to write the equation for the drain current. So this is the formula for drain current. So this diagram, which is like this, remember this maximum point is IDSS, and this minimum point of on the voltage axis is VGS off. So if we're able to identify that this is IDSS, this is VGS, and substitute that into this equation, we have IDS is 12 in bracket 1 plus VGS is now given over VGS off is minus 5. So we have a minus here, and VGS is minus. So minus cancel, minus gives minus times minus will give us a plus. That's why you have a plus here. Now the next example says a JFET has the following parameters: IDSS, VGS off, VGS, find the drain current. So it's as simple as that. You just substitute in the values into that formula and simplify, and that gives us 6.12 milliampere. Another way, another example there is you are given the IDS as 5 milliampere, you are given IDSS as 10 milliampere, you are given VGS as minus 6 volts. You are asked to find VGS and VP. Of course, to find VP is as simple as finding a positive value of VGS, which is 6 volts. Then for VGS, you just have to simplify, make VGS the subject of the formula, and then you have your VGS as minus 1.76. Now, this time, you are given a diagram, and you are asked to determine the drain current, taking the values from the diagram. The formula still remains the same: ID is equal to IDSS, bracket 1 minus VGS over VGS of raised to square. So if you are able to identify the parameters given, all you need to do is to substitute in the values and simplify. Now, parameters of have a long way to go. Parameters of JFET. Like vacuum tube, a JFET has certain parameter which determines its performance in a circuit. The main parameters are the AC drain resistance, the transconductance, and the amplification factor. So the AC resistance is the VDS over ID at constant VGS. VDS over ID at constant VDS. The transconductance is finding the reciprocal. Now, remember that the AC resistance at constant VDS, but this time, transconductance is ID over VGS at constant VDS. So at any time, either VGS or VDS is constant for these parameters. Then this time, amplification factor, we have VDS over VGS at constant ID. So we are still playing around with these three parameters, which are VDS, ID, and VGS, those three parameters. At any of these main parameters, which is AC drain resistance, transconductance, and amplification factor, these three properties, VDS, IDS, VGS, one of them must remain constant. So here, VGS is constant, here VDS is constant, and here ID is constant. The relationship among the parameters. So you have the formula there. Here is an example. So once you know the formula, all you need to do is to apply them. So look at this formula. This formula is different from the ID formula. Take note of this. ID is equal to, let me write it out here so that you see it compared. ID is equal to IDSS one minus VGS over VGS of square. This has a square, but this does not have a square. And GMO is not the same as IDSS. So note these two formulas, there are differences between them. GMO is 2 IDSS over VGS off. and GMO is the transconductance at VGS 0. So note the difference between the two formulas. And there are examples that you can practice and then get yourself familiarized with the formula. Now, biasing. We have basically two types of biasing, and the two types, the second one has equally two types of biasing within it. So the first one is bias battery. In this method, JFET is biased by a bias battery. This battery ensures that the gate is always negative. This is nonsense. So So we have self-bias and potential divider method. We have talked about, though this is under FED. So connections, unlike BJT, where we have common emitter, common collector, and common base. For JFET, we have common source, common gate, and common drain. However, the most commonly used is common source. Most commonly used is common source. The common drain, common gates, of course, you hardly find them useful because the current will have to flow through source to drain. Source to drain. So if I make gate common, I make drain common, it may not give what is expected. So this is a common source connection. Then this is a voltage divider circuit. Voltage divider. You have seen this kind of circuit before with BJT. So this is load line analysis. Remember that your load line is a line that joins your saturation point to the cutoff point. And within the line there, you have your operating point, which is the quiescent point. So for JFET, you have that expression. VDD is equal to VDS plus ID in bracket RD plus RS. That is this for voltage divider. So at maximum, we have VDD over RD plus RS. If we consider that, remember that the conditions for getting the maximum current is that one parameter will be 0. Then to get the point on the voltage, the current parameter will be 0. So here, if VDS is 0, it means that we are going to have this cross the quality sign. So if this crosses the quality sign, we have VDD is equal to ID in bracket RD plus RS. So if we make I the subject of the formula, we are going to have this expression. So the point on the ID axis where we have this is here. Then to find this point, point B, it means that I will be 0, the current will be 0. So if the current is 0, it means that VDS is equal to VDD. So that is what we have here. So that is how to find your points, how to plot your load line graph. So that is what is explained here. So these is an example, and then these are solutions. So don't worry, we are rounding up. Now, so we have like 4 more slides. This is the MOSFET. So we have 2 types of MOSFET. We have the depletion type and the enhancement type. So I will send a slide to you to go through it. Now, before we call it a day, I sent assignment to you people. I hope everybody has gotten the assignment.
Yes, sir.
So do you have any question on that assignment so that I can clarify it with the remaining time? Do you have any question on that assignment?
I have a question, sir. Good morning, sir.
Yes.
The circuit diagram, we have to follow it strictly, right?
Not necessarily. Anyhow you want to do it, that will be okay for you. No problem. But I gave that circuit diagram as a guide.
Okay, sir.
A
And
guide.
also for the NPN, we have over 19 values for V in.
Yes.
Which is the same as our VBE. So we should use the whole of the 19 values, or we pick from those 19.
Yes, all of them.
Oh, okay, sir.
All of them.
Thank you, sir.
So that you plot a graph. So the instruction, I put instruction in that assignment. That instruction should guide you. So,
Okay, sir.
Yeah.
Thank you.
yes. Now, listen,
Okay.
to find your what I'm doing. When you want to find your current here, don't connect the second one. So if I simulate now, okay, let me just teach you how to, you can see the plot, isn't it? So the plot
Yes,
will guide.
sir.
So when you want to get this kind of plot, just to guide you to see if you are doing the right thing, you come to simulate. Look at what I click there, simulate. Then click analysis and simulation. When you click analysis and simulation, then you come to DC sweep. DC sweep, and then you set your VC and VBB. Then go to your output, pick I Q1 in bracket IC, move it to, but you don't even need this. You don't even need it. What you should do is, when you want to find the reading of this first one, don't connect this. If you connect the two at a time, you will get different readings. So find this, find the I here, then disconnect this.
So,
Disconnect this, and then you connect this.
please, I have a question.
Yes.
Okay, and when taking the readings of current, how to connect the ammeter in series with the resistor, or we can make it parallel like this.
Is that what? Come again.
Okay.
When taking the readings from the ammeter, sir, when we want to take our readings of current, like can we position it this way in such a way that the ammeter will be parallel to the resistor, or we have to make it in series?
You can do you can connect the ammeter anyhow. So far as it is giving you reading like this now, it can be like this. But if you connect it like this, that means you connect this here, connect this here. It does not change anything.
Okay, sir. Okay, sir.
It does not change anything.
All right, sir.
So what you are varying is VB, B, and VCE. That's what you are varying. Then you find your readings and plot your graph. So send it to me by Tuesday next week on a single file. Don't send two on a single file. Put everything, copy everything to Word and send it to me on a single file. Your name, matric number, and department.
All right, sir.
Okay, bye-bye. If you don't have the software, you can still come or meet classmates. You don't have any excuse. Oh, don't tell me that because you don't have any software. I've been announcing, I've been saying it. If you don't have, come and meet me or meet any of your classmates that already installed the software.